one of calculus's most enduring questions is how to find maxes and mins of functions, how to optimize things. You did a ton of this in BC, so let's try it in multivariable. Before we get started, a couple things to deal with. The first is the difference between what we'll call absolute versus local. So this is the question of whether a max or a min is a local one or is the absolute max or min for the whole function. So let's take this simple little graph here. We have here right in the middle, we have a local minimum. And we can tell it's a local minimum because the curve dips down and then comes back up. It's a local little point where our function is low. We also have a local maximum over here. Over here we have another maximum, but this is the highest point of the whole function. This is our absolute maximum. So we have an absolute maximum, a local minimum, and it's actually important to note that the function that I've drawn here does not have an absolute minimum. Because as far as we can tell, it continues down on both sides. So this does not have an absolute minimum. You're not guaranteed to have any of these on a given function. The second point that we need to make is how do we find maxes and mins? Well, back in the day, we demanded that our derivative be 0. So what we're going to say now is that if a point, AB, is a max or a min, we'll say is an extremum, we're finding extrema of the functions, of f of x, y, then it has to actually be the case that both fx and fy are equal to 0. That is, maybe put a little bit better, the gradient of f at AB needs to be the 0 vector. And that's maybe one way to think about that is that, you know, if you're at the maximum, you can't go uphill anymore. There's no direction that's uphill. Or if you're at the minimum, every direction is uphill, so there's no special direction. So our gradient has to be 0. And these points have a special name. Points like this, where the gradient is 0, have a special name. These are called critical points. Critical points. It's worth noting, not every critical point is a max or a min. So the question is, how can we tell whether a critical point is a maximum or a minimum? So let's take a little example here. Let's take as our example the following function. F of xy equals x to the 4th plus y to the 4th minus 4xy plus 1. All right, so let's see first if we can find all the critical points for this function. Well, if I take fx here, I'm going to get 4x cubed minus 4y, and I want that to be equal to 0. Fy, I get 4y cubed minus 4x, and I want that to be equal to 0. So I end up with these two conditions, x cubed equals y, and y cubed equals x. So the question is, what are the solutions to the system of equations? As might be clear, 1, 1 is a solution. Negative 1 is a solution, and our third solution here is 0, 0. So we actually have 3 potential critical points for this function. So and now what do we do? How do we actually figure out whether any of these critical points are the ones we want? And here's where we're going to introduce a new version of something, again, you had in BC Calculus. Because in BC, if you wanted to know whether something was a max or a min or neither, you looked at the second derivative, right? If the second derivative were negative, it was a max. If the second derivative was positive, it was a min. If the second derivative was 0, then it was a little flat point like on x cubed. Well, we have a similar, a kind of a new version of the second derivative test, which is a touch more complicated. So this is how we test our critical points. What we do is for each critical point, we calculate the following thing called a discriminant d. And the way we calculate that is fxx times fyy minus fxy squared. So and then what you do is you calculate that discriminant, and then one of, I say three, but really one of four things happens. Either your discriminant is positive. If your discriminant is positive, then you have another decision to make. If the discriminant is positive, and your second derivative, fxx, or it could be fyy, it doesn't have to be fxx, is positive, then what you have is a local minimum. What you have is a local minimum. And notice, again, our second derivative being positive is the same that we had before. You could also have that your discriminant is positive, and fxx, again, or fyy, it doesn't have to be fxx, is less than 0, in which case it's a local maximum. Local max. You could also have your discriminant be less than 0, in which case it is neither a max nor a min, in which case it's what's called a saddle point. And a saddle point is this very special little point that is neither a maximum nor a minimum. And our classic example is, if you think about back to our old hyperbolic paraboloid, x squared minus y squared. Here's a little sketch that I've made. The origin for x squared minus y squared is a saddle point, and you can do that test yourself. And why is it a saddle point? Well, one way to think about a saddle point is that from one perspective, it looks like a minimum. If I kind of approach it this way, it looks like a minimum. But if I approach it the other way, it looks like a maximum. So a saddle point is neither a true maximum nor a minimum. And it's kind of equivalent to like that little, those points you would find sometimes in BC calculus that are just like locally flat but are neither true maximum nor minimum. Some of you may be looking at this and saying, okay, d greater than 0, d less than 0. What if d equals 0? And if d equals 0, which doesn't happen very often, at least in our tests, if d equals 0, the test fails. That is, we don't know whether it's a maximum or a minimum, and you're going to have to figure out some other way to do it. That doesn't come up very often. So let's go ahead and interrogate these three critical points for our function and see what we can get. Let's go ahead and calculate fxx. Fxx here should just be 12x squared. Fyy is 12y squared. And fxy here is negative 4. So that means that our discriminant looks like 144 x squared y squared minus 16. So I just want to point out that if we plug in 0, 0, we get 0 minus 16, negative 16. So 0, 0 is a saddle point. If I plug in 1, 1, I get 144 minus 16, which is 128. And notice our second derivatives, fxx and fyy, are always positive, 12x squared, 12y squared. So this is a minimum. And similarly, negative 1 also gives me 128. And is also a minimum. So we have three critical points, a saddle point, and two minima. If you actually go ahead and graph this function, it kind of looks like this. Let me choose a distinctive color. It actually kind of looks like this. You get So you get something that's kind of got these two bulbous points downward and then goes up on either side. So there actually is no maximum. There's no maximum. It goes up to infinity as x and y get bigger. We've got two local minima. And then right there in the middle, some people think this looks like the pants of the bottom half of Patrick from SpongeBob. Right there in the middle place would be our saddle point. Because again, if you kind of go from leg to leg, it looks like a maximum, but if you go front to back, it looks like a minimum.